Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks problem of the day, and today's problem is count all possible path, and it is a medium level problem. So the problem basically says that we have been given an undirected graph in the form of this adjacency matrix. We have to find out whether it is possible to start from any node x and return to it after traversing all the vertices at least once and using each edge exactly once, right? So you can start from any node. The only condition is that you have to go back to that particular node. You have to visit every vertex at least once. That means no vertex should be left unvisited, and you have you need to traverse each edge exactly once. Now this part is very important, that each edge should be traversed exactly once, right? That means basically you will have to take all the edges inside this particular adjacency matrix. Now how can we actually solve this problem? You will see that this is a fairly simple observation. If you want each edge to be traversed exactly once and you want to go back to your original node x, whenever you enter a node, you must find some way to leave it, right? Or in other words, whenever you leave a node, you must find some way to enter it again. So let's say whenever you enter a node, you must find some way to leave it, and whenever you leave a node, you must find some way to enter it, right? These two statements are applicable at different situations. Let us see how. So let us see the first situation when you enter a node, or let us see the second one first. This is where we start from. When you leave a node, you must find some way to enter it. Let's say this is the node x. You left a node using this particular edge. Your condition says that you want your traversal to end at this particular node x only, right? So there must be some edge coming to x, right? Or if you are leaving at two places, right? If you leave from one here, then you must have at least one more entering edge like this, right? So basically when you leave using one edge, there must be some other edge with the help of which you can re-enter this particular node so that your traversal can end at x, right? So coming to this particular statement, whenever you enter a node, you must find some way to leave it. So basically this was your x. You exited this particular node x to reach this particular node. Now you don't want your traversal to end at this node, right? So you might want to exit this particular node, or in other words, you have to exit this particular node because you cannot end your traversal here, you cannot stop here. So basically again, if there is one node, one edge coming to it, you need some edge going out of it. Since each edge can only be used once, when you use this edge to come inside it, you cannot use it again to go outside of this particular node, right? So with both the observations, we can conclude that the degree of each node must be even. So it can be either of these cases. Either you have entered a node and you want to leave it now, or you have left this node, you want some way to enter it again, right? So in both of the cases, the degree of each node must be even. So let's say you exited this node once and then you entered it, right? So these two edges cannot be used again. Now you exited once more, now you will have to enter this node once more, right? So again, the degree should be even in all the cases. Now let us consider a case where the degree of all nodes is even, but you cannot still visit all the vertices. Let's say we have a graph like this, right? And one of the nodes, or let's say three nodes are like this. So you can clearly see that all the nodes have even degree. So this has 1, 2, this has 1, 2, this has 1, 2 here, and similarly all these three nodes will also have the same degree, which is 2. Now all the nodes have even degree here, but if I start my traversal from here, I cannot reach any of these vertices, right? So basically our graph should also be connected. This is our second condition. So let me write it here. These are the two conditions. First, the degree of each node should be even. The whole graph must be connected, right? These are the only two conditions that you need to make sure in order to satisfy all the constraints that are given in the problem. So if I do it like this, now the degree of these two nodes have become odd. So I'll need to make some other edge as well. I can make it here and I can make it here, right? Now I believe the degree of all the nodes are even and they are connected as well. So these are the only two conditions that you need to take care of in order to satisfy the problem, right? Now let us see how we can implement it in code. So what I've done is I have first of all taken the path of or the n value, that is the number of vertices in my adjacency matrix. Now I've created an n degree vector, which is basically the degree of the nodes. I've created a visited vector, all initialized with 0, and I've created an adjacency list of the graph. Now creating an adjacency list is not at all important. You can also traverse in this original adjacency matrix as well. I just created it for my convenience. Now what I do is I'm just going through all the nodes. If paths of ij, that means if there is a path from I to j, I'm pushing back this particular node j into I and incrementing the value of j or the in degree of j, right? Why am I not incrementing the in degree of I here? Because if ij is true, ji will also be true. I can increment the value of I there, right? So I only have to increment it once. I don't increment it twice, so that I only use this once here. Or maybe what I can do is I can push j inside I can push I inside j, increment both the in degree of ij and mark my paths of ji as false, right? So that I do both of these things here and I don't increment there at the second time, right? So either way is fine. This one, all this works fine. Just make sure that you don't make double entries. Now I've initialized my odd variable with 0 and my cc variable with 0. So odd variable will denote, is there at least one node whose degree is odd, right? And my cc will denote the number of nodes inside my current connected component. So I can start my traversal from any node, literally any node. I just want all of them to be connected. So if I start from 0, my connected component or the number of nodes in my current component should be equal to n. Even if I start from any other node, the answer should always be the same, right? Now not odd, basically that means there should be no nodes, or there should be no node basically with the in degree or the degree which is odd, right? That is why I have not odd here. Now inside my DFS function, if I show you my current node as visited, I mark my odd as odd, logical or in degree of node and 1. That means if the in degree of my current node is 1, this whole odd variable, or if my in degree of my current node is odd, this whole odd variable is going to be true. And once it becomes true, it is always going to be true forever, because I'm using a logical OR condition. Now I increment my connected component count here, and for all children that have not been visited, I just call my DFS function. So at the end, if my current connected component is equals to n and I don't have any nodes which have the degree odd, that means I can return true. So this was all about this particular problem. Let me just quickly submit this and show you that this particular code works and this solution is absolutely correct. So you see, this passes all the test cases and this solution is correct. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video. Don't forget to share thoughts in the comments, because your engagement with this video really helps YouTube algorithm to understand that this video is actually helpful for you, and it will be able to reach much more people like you who want to keep solving new problems. So that is it for today. Till the next video drops, keep coding, stay safe, bye bye.